Welcome to this explainer on vacuum contactors. Now, if you work around marine electrical systems, you probably already know that a vacuum contactor is a seriously brilliant piece of hardware. I mean, it's fast, it's clean, and it's nearly maintenance-free. But, and this is a massive but, it carries one hard limitation that you can never, ever forget. Because if you do, it could quite literally destroy a ship's electrical system. So let's start with a crucial check. Put yourself in this scenario for a second. What is the true risk if a shipyard tries to, say, save a little money by skipping fuses on a new installation, specifically on a circuit with a massive 1,000 MVA fault level available? Well, the result is catastrophic destruction. You see, while vacuum contactors use incredible interrupter technology to control AC motors, transformers, and power factor correction banks, the contactor itself actually has a very limited short-circuit breaking capacity. Without fuses stepping in to intercept, a real short-circuit fault would instantly destroy the contactor, and honestly, potentially take the entire switchboard section with it. Fuses are absolutely mandatory in every marine installation to handle these massive fault levels. The contactor alone simply cannot break them. To make sure you master this equipment, our explainer today is going to cover 4 key areas. First, the hard limitation. Second, a breakdown of the V7/ZC spec sheet. Third, a look inside the vacuum bottle itself. And fourth, fail-safe fuse mechanics. All right, let's jump into section 1, the hard limitation, and exactly why those fuses are mandatory. The numbers really back this up. The V-contact is fantastic for switching because of its sheer precision. It's got a closing current of 2.4 kiloamps and an extremely low chopping current of half an amp or less. And that ultra-low chopping current is vital, right? Because it prevents dangerous overvoltage transients in your motors and transformers. But take a look at its interrupted current capability. It's only 400 amps. That right there is exactly why those fuses are non-negotiable for handling massive fault currents. Now, where the V-contact truly shines is its endurance. This single number, 100,000 operations, defines its mechanical and electrical lifespan. You are getting 100,000 closing and opening cycles with virtually zero maintenance, all thanks to those sealed vacuum bottles. Moving right along to section 2, let's look at the V7/ZC spec sheet. When a commissioning spec calls for a V7/CZ model, these are the 4 exact numbers you must verify before you connect a single wire. First, a nominal current of 400 amps at plus 40 degrees Celsius ambient. Second, a nominal voltage of 7.2 kilovolts. Third, the associated fuse needs to be rated at 315 amps with a short circuit capability of 50 kiloamps. And finally, your control devices, like the closing electromagnet and shunt trip release, operate at 230 volts AC. Now, check out this deliberate mismatch on the specs. Did you catch it? The contactor is rated for 400 amps, but the associated fuse is actually rated lower at 315 amps. This is definitely not a typo. The fuse needs to clear a short circuit incredibly fast and cleanly, well within the contactor's 400 amp thermal and mechanical limits, before the contactor itself can take any damage. So let's do a quick check for the engineers out there. Say a spare parts order arrives on the deck plates for your V7/Z unit, but they sent a 400 amp fuse instead of the specified 315 amp fuse. Is this a safe substitute? Absolutely not. You should never substitute fuse readings in this system. Swapping to a larger 400 amp fuse completely removes that critical safety margin. It breaks the deliberate coordination scheme that protects the contactor during a fault. If you were to install that 400 amp fuse, your contactor might actually melt down before the fuse even thinks about blowing. Okay, let's shift gears to section 3, inside the vacuum bottle. Let's actually crack open that vacuum interrupter to see how it pulls off 100,000 operations with zero service. Inside every V-contact pole is a sealed bottle made up of 5 core parts. You've got a robust ceramic housing for mechanical strength and insulation. Inside that, there's a moving contact and a fixed contact where the actual electrical connection happens. Surrounding them is a metallic screen. And finally, a seal membrane bellows. This is a genuinely brilliant piece of engineering that allows the moving contact to travel up and down while maintaining a perfect, absolute vacuum inside the bottle. And right here, we find the true hero of the bottle, that metallic screen. You see, every single time those contacts open under load, an arcing event vaporizes a microscopic amount of the contact metal. Without this screen, that metal vapor would eventually settle on the inside of the ceramic housing, clouding it over and destroying its insulation strength. But the metallic screen catches that vapor, keeping the ceramic clean and strong over decades of use. It's the exact reason that 100,000 operations is a reality, not just some marketing claim. Finally, Section 4, Fail-Safe Fuse Mechanics. So the fuse holders on a V-contact are actually tied to an integrated release mechanism. If a technician forgets to install a fuse or maybe removes one for testing and leaves it out, the contactor is physically prevented from ever closing. It literally blocks the mechanical action. And why is that? It's to protect your motors. Because if the contactor could close with a missing fuse, your three-phase motor would run single-phased, which would quickly cause it to overheat and just completely burn out. One last quick check to wrap things up. If one fuse blows during a fault on a three-phase V-contact, what exactly happens to the contactors on the other two live phases, assuming the release mechanism works correctly? The answer? One blown fuse trips all three phases open, every single time. It is never partial. The mechanism doesn't just isolate the blown fuse's phase, it trips the entire contactor open. This instantly keeps your motors safe from single-phasing and completely isolates the downstream circuit. Now think about this for a second. If these physical and electrical interlocks are this meticulously designed just to manage a vacuum contactor's limitations, what happens to a ship's multi-million-dollar propulsion system when a single engineer decides to bypass a safety mechanism just to save time? The sea has a funny way of always finding your shortcuts. So what other silent safeguards are currently protecting your ship right now? Thanks for tuning in to this explainer, and stay safe out there.